Well, good afternoon, everybody, and welcome to today's final webinar from Smart Vision Europe. And the final topic of today's webinar series is to look at Bayesian analysis with SPSS. My name is Charlotte Quinn. I'm an analytics consultant at Smart Vision Europe. If you haven't joined any of these sessions before, you should be aware that they are recorded, so you'll be able to listen to them again. And there is quite a lot of slideware in here because there's a lot of theory. We need to explain a lot of the terminology and concepts behind Bayesian analysis. So you'll get a copy of the slides. We'll email out a link to you to download the materials after the session has ended. If you find it particularly useful for colleagues who are unable to attend today, and you can get enough of them together, it may be possible for us to rerun it, on a private basis. The best thing to do is just to send us an email or something like that, and we'll see if we can do that. Now, with regard to asking questions, all the lines are muted, so I can't hear you. But if you use the chat panel, my colleague Rachel, who's also online, will be monitoring that as we're going along. And then if there's any outstanding questions at the end, I'll try to make sure I get through this at the end so that we can answer any outstanding questions. However, it is quite common for people to have questions after the session's ended and to email us separately. So feel free to do that or to reach out as and when any questions occur to you. I'm quite happy to answer them. If you don't know who we are, we're Smart Vision Europe and we are a technology company. We're a gold accredited partner to IBM. And we specialize in IBM's case, in the SPSS and Watson Analytics portfolio of products. We're also a partner to Predictive Solutions and to Data Robot. And as a company, we specialize in statistics, data science, advanced analytics, big data technologies, AI, all that type of stuff. Though we don't just work with manufactured products, we also work with open source technologies like R and Python, as you would expect. We're a relatively small organization, but we're a team of people who have a very deep and long experience working in the advanced and predictive analytics software and technology industry. I started working for SPSS in 1995, as did my colleague Rachel started, I think, the following year. So we've all got about, 25 years plus experience working across many different applications in pretty much all possible sectors, both commercial and not-for-profit, of applying statistics, analytics, data science to a range of different problems and different challenges. So whatever sector you yourselves work it within, we've probably got some experience of applying at least some statistical know-how or AI or machine learning or data science type applications within that area. As a result, we're going to talk about SPSS today. We're going to talk about Bayesian analysis within SPSS. And we have to introduce this within the context of what we call the two paradigms. In the earlier webinar, I was talking about significance testing, and I was very much working within and speaking within the context of what was known as the frequentist tradition. The frequentist tradition is basically the type of stats that most people are taught at universities. Maybe not so much these days. I suspect it's a bit broader, but certainly if you've been taught in the last, I don't know, 10, 20, 30 years, something like that at uni or at school about statistics, they probably taught you the frequentist approach. And the frequentist approach is the world of p-values and rejecting or accepting the null hypothesis and all that sort of stuff. And it's a particular approach to statistics. It belongs in a particular world. But in fact, there is an alternative way, and the alternative way is the Bayesian approach. So the frequentist approach is often characterized or populated by greats of the statistical world, such as Ronald Fisher and Carl Pearson, Egon Pearson, Jerzy Neyman, people like that. And these guys came up with a number of techniques and a number of tests and approaches and sort of procedures and a language to talk about statistics. So they talk about significance. They talk about, a alpha level of 5%, 95% confidence intervals, all that type of stuff. They're very much responsible for the furniture of that world of statistics. The Bayesian approach is completely different, as if the frequentist approach never existed, and it's named after the Reverend Thomas Bayes, who would, if he'd lived long enough, would have been very surprised to discover that an entire paradigm of statistical inference was named after him, because he certainly wasn't a statistician. He was a mathematician to a certain degree, and he was interested in this, at least fleetingly, in the idea of uncertainty and how you would account for uncertainty and how you would estimate uncertainty around that, and came up with a theorem, almost a footnote, which was then picked up by some quite well-known mathematicians long after his death, and used as a foundation for a different approach to estimating parameters, effectively to estimating whether or not something is going on, which is really what statistics is about, trying to account for variation and to say whether or not something is going on and to estimate the likelihood of something occurring or something being true. So the frequentist versus Bayesian paradigms, that's the word we're talking about. There has been an increasing use of Bayesian techniques in research articles over the last few years. That's why we're really talking about it, because it's become a much hotter topic. And people within the world of research, of course, tend to copy one another. So it's become, the number of articles published using Bayesian statistics has increased almost exponentially over the past 30 years or so. One of the reasons why it's come about is a lot of Bayesian techniques require um, more intensive computing than that perhaps was available to most people, say in the 1950s or 1960s or 70s. One of the reasons why people like Fisher and Carl Pearson, became so popular was because they published tables of values such as chi-square values and other statistical distributions, which meant that people could calculate statistics by hand, you know, and a lot of computing technology such as SAS and SPSS and Statistica and stuff like that really just speeds up what was designed to be calculated by hand. A lot of Bayesian stuff requires quite intensive resampling of data, and as a result of that, wasn't always practically possible to be calculated by hand. So as a result of that, I guess the frequentist statistics kind of got a head start while people were waiting around for computing technology and personal computing technology to become available. It's also regarded as better at dealing with smaller samples. A lot of uh, frequentist statistics, we talk about asymptotic probability values and that sort of stuff, which basically means we can assume this is accurate if if your sample's large enough and representative. It's the size of the sample size really does affect the reliability and the statistical power of procedures when we're working within the frequentist classics of the tradition where we're running t-tests and things like that. A fourth element is what's called the replication crisis. That's been a term that's been used in recent decades, really very much within the social sciences, especially psychology, to denote the fact that a lot of classical social science and psychological experiments cannot be reproduced when you basically rerun the experiment, you're finding that you're not getting the same p-values out of it. Something which was statistically significant beforehand is no longer significant now, and some people have blamed that on the p-value being set at a too high a level, at 5% being too easy a threshold, a 1 in 20 chance of making a type 1 error. That's just too easy, and it's going to lead to people, reaching the wrong conclusions. So that's probably put a bit of pressure on it. Some people say there's a greater flexibility when it comes to experimental design. Some experimental design procedures can be quite involved, where you've got a lot, quite an involved experiment, and that can be difficult and requires a lot to calculate using frequentist statistics, and it may be quite demanding with regard to the size of the samples you need to get to compare with one group against another. And some people say, look, p-values really are they're old hat now, and accepting or sorry, rejecting a null hypothesis, or not rejecting a null hypothesis based on whether or not a number is above or below an arbitrary threshold. It's kind of, it's not very nuanced. It's not very intuitive. I've heard people say, "Oh, it's really significant," as if a significance value was a sort of effect size. It's a bit like saying it's really dead or it's really alive. Um, it's one or the other. Whereas Bayesian approaches do offer a way for you to weigh one set of evidence against another, almost as a ratio. And some people say this is just a lot more intuitive, and it's a more intuitive sense of weighing the case for one outcome versus another. And lastly, it should be said, it is incorporated a lot into a lot of machine learning algorithms. The concept of Bayesian, you hear a lot of mentions of Bayesian chains and Bayesian techniques and Bayesian classification in a lot of modern non-statistical but machine learning algorithms, which are underpinning, say, a lot of AI type applications. So, what are the differences between frequentist and the Bayesian approach? Well, there are some fundamental philosophical differences. So, in the frequentist approach, probabilities are related to how frequently something occurs. That's what a frequentist means. It's based on frequency. How often would you see a result as extreme as that, assuming that there's no relationship between these factors. Whereas with the Bayesian approach, it's a bit more subtle. It's all related to certainty or uncertainty of something. It's a little bit more vague than that. It's about the evidence that exists out there in the world. In the frequentist approach, because it's based on frequencies and probabilities based on frequencies, it's basically everything is based on the data and the data that you have, the sample you've collected. Whereas the Bayesian approach says, yeah, the data is really, really important, but the context and whatever is our current understanding of that situation is important as well. This is extremely, controversial when it comes to frequentist approach. Who says, what you're doing is you're just allowing received wisdom to kind of pollute your analysis in there. When we get down to the sort of brass tacks of it, in the frequentist world, the parameter is a fixed value. So we talked about this in the last session where we said, in classical statistics, you're using statistics to try and estimate a parameter value, the mean blood pressure of all adults aged 18 or over in the UK at this exact second. And the idea is that that is a number. It's a number, it's there, and you're trying to estimate that number. Whereas the Bayesian approach says, no, it's not. It's more like a sort of random variable. It's like a distribution where one value is the most likely. So it's almost like a sort of subatomic approach to it, if you know about subatomic physics, where you might not know the momentum and direction of an electron. Everything's probabilistic. So it's saying the parameter is this fuzzy thing which has a single most likely outcome, but it could take other forms. It could be other values. It's not a single value. It's more of a distribution, which is very interesting. The frequentist approach, therefore, is that the truth is fixed, the parameter is fixed, but the estimation is uncertain. So the model changes, but the thing you're trying to estimate remains out there somewhere in the fog. Whereas the Bayesian approach is completely different, saying no, no, the thing that's out there in the fog is foggy, and the estimation that you're using for it is fixed. So whatever model you're using is fixed. That doesn't change. You're just trying, it's just like, using a telescope, but the telescope doesn't change even if the object that you're trying to look at is ill-defined. In the frequentist approach, a lot of people don't realize the frequentist approach when you're dealing with p-values. It only says something about the null hypothesis. It never says anything about the alternative hypothesis. You can only reject or not reject the null hypothesis in the frequentist approach. You can't do anything else. It's very one-dimensional. Whereas in the Bayesian approach, it actually considers information about the null and the alternative hypothesis. The idea that let's say you imagine that left-handed people had faster reflexes than right-handed people. That would be your alternative hypothesis. The null hypothesis would be no, they don't. Left-handed people do not have faster reflexes than right-handed people, or there's no evidence to show that there's a difference or something like that. And so the Bayesian approach tries to weigh up both. And as a result of that, the frequentist tradition, as we know, only uses the collected data, the data that's in your sample, that's in your SPSS uh, data editor, doesn't use anything else. Whereas the Bayesian approach uses the collected data and an estimate of the truth in the absence of any data. This is easily the most controversial aspect of it. This is called the prior probability. It basically says, no, let's not assume that the data could be anything. Let's be sensible. But what have other people said in the past? What does previous research indicated? What does our understanding of the world indicate? So if we were to take that to its logical conclusion, and we should bear in mind that both analyses will actually lead very similar results in the vast majority of cases, so you're unlikely to get a completely different result. If we take that to its logical conclusion and we look at an example of how this manifests itself, a classic issue would be look at confidence intervals. In the frequentist tradition, people pretty much always misinterpret confidence intervals. I used to type into Google in one of these webinars and type in live, in the webinar, what is the correct way to interpret the confidence interval? And the very first hit that came out was exactly the incorrect way to interpret confidence intervals. Most people think that confidence intervals are show you two numbers and it says that there's a 95% chance that the true value is between those two numbers. And that's not the case. It's much more involved than that. It's actually subtle. It says that there's a 95% of the confidence intervals that you calculate will contain the true value. And that's not the same thing, believe it or not. I know it might feel like it's the same thing. It's not the same thing. So it's basically saying, look, if you recalculate the confidence intervals again, 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 95% of the confidence intervals that you calculate will contain the true value. But with the Bayesian approach, what you're saying is that there is a 90 that the credible intervals you're creating, which is what Bayesian calls confidence intervals, credible intervals, the credible intervals show that there's a 95% chance that the true value lies within those intervals, which in other words, what most people interpret frequentist confidence intervals to be and misinterpret it actually applies to the Bayesian approach. I remember during the COVID crisis, there was a lot of discussion over the R value, which is the rate at which the COVID disease spread. And whenever you looked up government statistics, they always showed credible intervals. That's probably the influence of the Professor David Spiegelhalter, who's a very eminent statistician. But the other reason is because credible intervals are just much easier for people to get their heads around. It's just it makes much more intuitive sense to say, oh, these two numbers we're coming up with here, let's say it's 1 and 1.2. We don't know what the true R value is, but there's a 95% chance that the true R value is within that range. Whereas if you're taking a confidence intervals approach, you'd be saying that 95% of the intervals that you generate will contain the true R value and intervals of this nature. And that's just much harder for people to get their heads around. We can also push this to its and take it apart and see it in terms of how the Bayesian approach turns the frequentist approach up on its head. Because in the frequentist approach, the thing which is variable is the confidence intervals. What the frequentist approach says is don't get hung up on these confidence intervals, because if you rerun this analysis, you'll get different confidence intervals. So they're variable. But the thing that you're trying to estimate, the true value, the true R value, it's out there and it's fixed. So whereas the Bayesian approach says, no, 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 the true R value isn't like 1.1 or something like that. It's kind of 1.1 is the single most likely value, but in fact it's a distribution of values. And the credible intervals are effectively fixed. They don't change. So you should interpret them literally. So it's a very different approach philosophically. In one, the model varies, that's the confidence intervals, but a parameter is fixed. In the other, the parameter is variable, but the model is fixed. The model is kind of like you've constructed the model, it stays. It's not something which is fuzzy or variable. Which means we have to talk about prior and posterior probabilities, which is right at the heart of the Bayesian approach. The frequentist approach does not use prior probabilities. It only uses collected data and nothing else. The Bayesian approach includes the calculation of prior probabilities the probability of the event occurring based on established knowledge or beliefs. And in fact, it has to use those. It uses them whether you like them or not. It will always use them. And this is obviously, something which is pretty important distinction between one approach and the next, and something of a, as I say, an area of controversy and argument between the two paradigms. So if you take things again to the logical conclusion, say, let's take an almost silly example, say, what's the probability of a coin landing heads? And we flip the coin. If you were taking a frequentist approach literally, if you were taking it literally, really at face value, and you say, I said, I don't know what the probability of a coin landing heads if I flip it, heads or tails. What you're effectively saying is it could be anything. It could be 100% likely to be heads or 0% likely to be heads or anything in between. Until you collect the data, you don't know. That's what it's saying. You have to collect the data. The only way to find out is through the data, and you don't pay any attention to the fact that the coin looks like a coin. And it looks fairly equal on both sides. The Bayesian approach would be a little bit softer. It would say, look, it looks like there's only two outcomes, and the coin looks fair. I can't imagine it landing on its side. I can't imagine it landing 100% of the time on one side and 0% of the time on the other. It might be sensible to assume that the initial probability, the prior probability, is it's 50-50. And then we'll collect some data and we'll update that data with our prior. That's what we're doing. That's what you update the data that you're collecting the prior. And that's a kind of a gentle approach to it. But the same sort of thing might be if you're looking at something like blood pressure and the effect of blood pressure and, I don't know, weight or BMI and blood pressure or salt intake and blood pressure. You're not doing it in complete isolation. There is a body of knowledge there that you might draw upon that says, a lot of salt in your diet would lead to, at least for some people, a higher blood pressure than those it wouldn't. That's what the current understanding is. Let's assume that it does have this minimal effect, and that will be our prior. Then we'll go off and collect some data and update it. That's the thinking behind it. So in Bayesian statistics, the prior probability is the probability distribution that would describe the likelihood of a given value before some new evidence is taken into account. Now, in this case, the prior probability distribution is just a binomial distribution with a 50-50 chance. That's what it would be for landing on heads. It might be a normal distribution where you say, I think the mean difference between these two groups is 3.4 or something like that. But it is a distribution. And as such, those working in the frequentist tradition have often regarded this as, more than controversial, as absolute heresy, really, in terms of its approach. The prior could be the expected proportion of people, for example, that are likely to vote in a referendum, or likewise, it could refer to the expected mean and standard deviation of an age distribution describing when people get married. You don't start up and say, I don't know, they might get married on average at 87, or they might get married at average at 15 or 16 or something like that, depending on the country. It's like you're probably going to have some notion of what the mean age is going to be beforehand. These prior probabilities could be based on past research, subject matter expertise, or reasonable assumptions based on the context of the study. So I just need to point out a couple of terms here that might pop up. I'm not really going to go into details here, but something that which you will definitely hear of is this term uninformative prior. And these are situations where no information is available as to the likely prior probability. And that's the default setting in SPSS. It just puts in an uninformative prior. If you don't give it a prior probability, it just says, okay, well, I'm just going to assume that everything has an equal chance, which is very, very close to a frequentist attitude. So it's often employed where you have absolutely no clue as to what the prior values are likely to be, what the mean difference is likely to be, what the proportion of people who are going to vote is going to be, what the difference in blood pressure is, what the correlation value is. You've got no idea. So examples include probabilities where every outcome is equally likely. And if you imagine that as a distribution, it just looks like a flat line because it means every value is equal. It's a kind of uniform distribution. If the prior and the posterior probabilities come from the same statistical distribution, they're called conjugate distributions, and the prior is called the conjugate prior. This is, again, I'm just pointing this out for terminology reasons. You may hear people talk about conjugate distributions. So it is possible that you're saying that I think that there's a binomial chance, and flipping a coin It's a binomial distribution, it's heads or tails. And when I've gone and calculated this with some new data, I've created my p-value, if you like, my prior probability, the chance that this is true, if you like, and that is also from a binomial distribution. Also seems to reflect that, seems to agree with the prior. They both seem to be related to binomial. The data supports that notion. Then that would be called a conjugate distribution, and the prior would be called a conjugate prior. This means they have to be both. Whereas if you assume that one was a normal distribution and it turns out that the data says, no, it's not a normal distribution, it's like a gamma distribution or some exotic distribution like that, it wouldn't be called a conjugate prior. So I'm really just pointing this out because these are terms which are used and that's what they refer to. A major criticism of Bayesian approaches is that there's no single prescribed, well-defined method for choosing a prior. No, there isn't. So, anybody can attack your research on that basis and say, well, why did he do that? But I guess one of the things that some Bayesian analysts would use as an advantage is say the good thing is I can play around the priors and I can say, well, let's assume it's like this, or let's assume it's much higher and it's like that. Let's assume it's this value or that value. They can play around with it and do a little bit of what if analysis, and then see what the effect is if the same problem. They can see how sensitive that problem is to the prior probability. It will be less sensitive the more data you collect. Obviously, the more data that you have, the less the effect the prior has, because the prior is kind of like your rule of thumb start point. And if you've got a ton of data, then it's not going to have as much an effect. The data will definitely swamp it. Posterior probabilities are the things we're trying to estimate. That's in the frequentist world, this would be your p-value, but here we don't get a p-value, we get a posterior probability. And the posterior probability is the probability results from updating the prior with the new evidence, with the new data. So you start off with your prior probability, you go and collect some data and you go, right, let's run the analysis, update the prior of the new data and see if this holds true. Again, I'm pointing out some terminology here that you might confuse you otherwise. The new evidence, this new data, the data that you've collected, the raw data that you put in the SPSS, sometimes referred to as the likelihood function. So when you hear it talking about likelihood function, it's talking about the data in your data set. So the posterior probability is equal to the prior probability combined with the new evidence called the likelihood, or the likelihood function. That just makes it easier for you. Okay, so how does it work? Well, it turns out that Bayes' theorem works when you just apply it to problems of uncertainty. Generally, you don't need necessarily even have to have a lot of data. It's one of the things that makes it quite powerful. A foundation for it is based on Bayes' rule. Bayes' rule consists of a hypothesis, evidence, that's data, effectively, E for evidence, and the relationship between that and the probability. So hypothesis and evidence. So it looks like this: P H given E is equal to P times H times so P times H times P times E given H, which is a mouthful, I know. But we'll just take it apart here. Just bear in mind that this vertical line in the middle of these parentheses here means given, means the hypothesis given the evidence in this case. And we basically will create this ratio of the probability of getting the evidence multiplied by the probability of that hypothesis being true, multiplied by the probability of that evidence being true given the hypothesis, which I know, again, sounds complicated, but we'll take it apart. So let's just break it down. Here's one. This is the probability of the hypothesis being true based on the evidence. So it could be, well, the example that's always given is that somebody thinks they've got a disease. They think they've got an illness. They think, oh my God, I've got all the symptoms of this disease. So, you'd say, okay, well, what's your symptoms? What's the probability of that hypothesis being true? And then the next thing is the prior probability of the hypothesis being true. Well, that would be like, well, how often does this disease occur anyway? Is it like 1 in a million times? That's something which, a frequentist approach doesn't do. Doesn't, people get terrified going on to Dr. Google because they think they've got all the symptoms of some awful disease without actually factoring in how rare that illness actually is and what your prior chance of getting it is. That's what pH is. And the next one is the probability of the evidence being true based on the hypothesis. So if what's the chance of getting that data, assuming the hypothesis is true? And the last one is the prior probability of the evidence being true. So what is the likelihood of that evidence being true? Let's take a nice silly example. Bernie thinks his metal detector has found a hoard of Saxon gold. So he's out in the field. He's got a really strong signal. What's the probability that that's true? Well, we could take it apart. We could say, well, the prior probability of finding gold. That's our first one. So we say, what's that? What's really, really small? You know, you're not likely to do that on many sessions of going out and with your metal detector, you know, every weekend or so. Um, the probability of getting that signal, if it was gold, because, you know, it could be some other really dense metal, could be platinum, could be even better, could be silver or something like that. Let's say it's 75%. It's a pretty good, pretty accurate, you know, signal. And then the prior probability of getting a strong signal in the first place. Do you get these strong signals all the time when you hit lead pipes and so forth? Let's say you don't, because it's a really unusual signal because he's really excited about it. The point is that we can take these three pieces of information, we can combine them together just in the fashion that we've done, multiplying one by the other, and it gives us a probability value. And that's why it's so powerful, because we can do this sort of rule of thumb sort of estimation. And it has proven to be, you know, in many different situations, to be very, very powerful. And the key here is that it's not just using the data. It's not just using the signal. It's using the prior probability. It's saying what's the likelihood of getting that signal to begin with, etc., etc. It's combining them together. This is the posterior probability that we're coming up with, okay? Okay, now we're about to do some Bayesian analysis now. But you just need to be aware that there's two different bits to Bayesian analysis. It comes in two different flavors. You can have them both together if you like, but there's two different outputs. One is this business of credible intervals we talked about already. I talked about confidence intervals and credible intervals. In the previous example, we introduced the fundamental principles of Bayesian analysis using Bayes' theorem. In particular, we saw how Bayes' theorem can combine evidence from new data, the likelihood, and prior probabilities to provide a posterior probability. The population parameters, however, that we might be estimating, and remembering these are not fixed values in the Bayesian world, they vary. They don't have to just be like, I don't know, is that gold or not? You know, it might be the difference between two means. Say, look, I'm seeing a difference here. It's not a very big difference. You know, is it notable? Is it important? Would regard it as so big that we would say that actually these two groups are different from one another? The blood pressure for left-handed and right-handed people, for example. Or it might be a proportional difference. It might be like, you know, I think that, you know, people in this ethnic minority group are more likely to vote, have a higher proportion of voting in general elections than this other ethnic minority group. So you might be looking at the differences between them. Or the correlation between travel distance and shopping frequency, you know. How often people shop in the supermarket multiplied by or as a function of how far away they live from it. So this parameter that you're trying to estimate isn't just an average. It could be the difference between average. It could be a proportional difference. It could be a correlation. It could be anything. So there's lots of different, depending on the test that you're running. In Bayesian analysis, we estimate a parameter's posterior probability by combining a prior distribution with the likelihood obtained from the data. We've already said this. Specifying a prior distribution is an important aspect of this process. Bayesian analysis will often return a mean estimate of the parameter value, such as the mean difference or the mean correlation. But really, as Bayesian analysis sees the parameter as a distribution of values, reflecting uncertainty, analysts tend to focus on credible intervals that encapsulate 95% of this distribution. Credible intervals are the Bayesian equivalent of the frequentist confidence intervals, except that here we can say that there is a 95% probability that the parameter lies within these bounds, something which we can't say with confidence intervals. Now, if the credible intervals estimated a range of values that related to some sort of difference between two groups, let's say left-handed and right-handed people and their blood pressure, think about what this would mean if the lower interval was a minus number and the upper interval was a positive number, such as in this example. In the SPSS output below, we can see the mean difference between the previous experience of clerical workers and managers. Although the overall estimate is minus 0.742, because the mean months of experience for clerical workers is 85, and the mean months of experience for managers is 77. It looks like clerical workers have more previous experience than managers. Maybe they're older or something like that. And that difference, if we take one away from the other, just depending on the order of the groups, it comes out as 7.42. It doesn't matter if it's minus 7.42. It's a difference 7.42. But the credible intervals here indicate that the actual range could be as low as 26 or as high as 11.26. And because one's a minus and one's a positive, we're saying, well, this difference could be positive or negative. It could be that the clerical workers have less experience than the managers, and the managers have more experience than the clerical workers, or it could be the other way around. This difference of minus 7.42 is not big enough. And this would be the equivalent of us saying we're rejecting the null hypothesis at this stage because we're saying, look, this difference could be positive or negative. There's not enough evidence to show that there is an actual difference because both numbers would be minus or both numbers would be positive. If I wanted to reproduce that in SPSS, I would simply go to SPSS here. I've already run a select statement here to get rid of one of the groups in the job category variable, which I've used in that analysis. If I just run it for you, run the descriptive statistics against it, you can see we've only got 363 clerical workers and only 84 managers. And if I wanted to run my Bayesian analysis that I did there, I just go down to, here we go down to is it general? That's a good question. Where have I put it? Oh, Bayesian statistics. There we go. And it would be an independent samples normal. That's the equivalent of a t-test, basically, or an equivalent of a one-way ANOVA, something like that. Because they assume normal distributions as well. So this would be independent test normal. And I'd hit reset here and I'd say, okay, I want to look at previous experience. That's my test variable. Then my grouping variable would be the groups that I'm comparing. And I would say I want to compare groups 1 and 2. Here, so it's going to be like a t-test, and that's actually group 1 and group 3. Because 1 is clerical and 3 is manager, which we can see here. 1 clerical, 3 manager. Custodial doesn't exist. It's been filtered out. And you can see here it says Bayesian analysis, characterize posterior distribution. This is the analysis that we've just done. There's another type of analysis here, which we'll come to in a moment, and you can see that you can run both. It says use both methods. So we click that. And there we have our value here, our posterior distribution, minus 7.42. We have our upper and lower credible intervals here from minus 26 and 11.26. So we would say, yeah, there's no evidence really to show that there's a difference here between the previous experience of clerical workers and managers. Now below that you can see some little charts here, and I'm just going to point out what these charts refer to. This chart here is for the clerical workers, and it says log likelihood. Remember, log likelihood means data because I was talking about the log likelihood here, so it's referring to the data. And you can see here that this peaks around about 85. So it's saying, yeah, it's like it's drawing a histogram saying 85 is the value we're seeing. It's got 363 cases here. So I'm going to assume the distribution looks like this, assuming it comes from a normal distribution. And over here, the value is 77 for managers. So it's very subtle. You can't see it, but the peak here is just a little bit lower, around about 77, going from 0 to 100 here. See this? Going from minus 100 to 300. And then the prior distribution, notice that it's just flat. It's 1. Because we didn't give it any prior values. We didn't say we think the difference is in fact 10 months. Or we think the difference is in fact 15 or anything like that. So it just came up with a non-informative prior, which we talked about earlier on. It's just a flat line. It says it could be anything. Everything's equal. Could be 0, could be 20, could be minus 30. That's very like a frequentist approach. Okay, so that's one way in which we can use Bayesian statistics to try to compare these groups. What else? It says, in other words, there's not much evidence that one group has more previous experience than the other. What about hypothesis testing? Can we not do that with Bayes factors and sorry, with Bayesian analysis? Well, it turns out in statistical inference, there is an important difference between estimating a population parameter and testing a hypothesis about it. They are separate things. I might say I think that population parameter, the average age of people get married is 26 or something like that. And testing a hypothesis would be, I think the average age of people getting married has gone up in the past, it's gone up in the past 10 years or something like that. In the previous example, we saw how the Bayesian estimations attempt to approximate a parameter's posterior distribution. Now we turn our attention to testing hypotheses using something called Bayes factor, in the same way we might do with a frequentist p-value. Now, in the frequentist approach to inference, much attention is focused on the null hypothesis. You remember this? This is when the p-value is calculated, and if it's found to be lower than the pre-specified level, called the alpha level, it's usually 0.05, sometimes it's 0.01. The convention is that we reject the null hypothesis. What we can't do with this information is we can't use it to accept the alternative hypothesis. The test simply doesn't consider this situation. You can either reject or not reject the null hypothesis. That's not the same with Bayes. With Bayesian approaches, you can compare the weight of evidence for alternative versus the null hypothesis. So what happens when the result is non-significant in a frequentist world, such as p.38? All that happens is the null hypothesis is not rejected. That's all that happens. And as such, the frequentist approach has very little to say about evidence for one hypothesis versus another. Whereas a p-value is used to reject or not reject a null hypothesis, Bayes factor compares the weight of evidence for the separate hypotheses by dividing one by the other. In SPSS, the resultant ratio of evidence attempts to quantify how much more evidence there is with a null hypothesis versus the alternative hypothesis. By doing so, it compares the evidence for both hypotheses, which is something that a frequentist p-value does not do. Now, in the Bayesian world, analysts use Bayes factors, or B, to indicate the relative strength of evidence for these two theories. Basically, it's just a ratio of one number to another. They're very, very simple ratios. For example, a Bayes factor comparing a null hypothesis to the alternative hypothesis would show that the data are B times more likely under the null than under the alternative. Whereas a B value is a ratio, it can range from 0 to infinity. But if the value is 1, then obviously if the value is 1, that means there's as much evidence for the null hypothesis as there is for the alternative hypothesis. It would mean they're equally likely. And we would therefore say, well, there's not much evidence that, one's true over the other. And that's very intuitive to us. Values greater than 1, indicating increasing evidence for one theory over the other, example, the null over the hypothesis, and values less than 1 show the opposite direction, increasing evidence for the alternative over the null hypothesis. Now, at this stage, unfortunately, in the world of statistics, the statisticians could not agree on which number you divide by the other. So you have two different Bayes ratio factors. One's called BF10, one's called BF01. And the BF01, you divide the null hypothesis evidence by the alternative hypothesis. HO is divided by H1. And BF10, you divide the opposite. It's the alternative hypothesis by the null hypothesis. So you need to know which one you're looking at. And rather confusingly, at least in previous versions, SPSS was using both methods depending on the test, such as one-way ANOVA using BF10. So anyway, conversely, Bayes factors with the label BF1 refer to situations where evidence for the null hypothesis is divided by evidence for the alternative hypothesis. In such situations, larger values indicate more evidence for the null hypothesis. So this is what you'll see when you go on to the help system in SPSS. It gives you a little table of values. And it says, look, if you're getting a Bayes factor and it's like between 30 and 100, then that's very strong evidence for the null hypothesis. Or if you're getting a Bayes factor between 100th and 1/30th, that's very strong evidence for the alternative hypothesis. So it's not just accepting or rejecting. And obviously, if you get a Bayes value of 1, it means no evidence whatsoever. And it gets really interesting because it's like, if it's 1/3 to a 1, that's 0.333 to 1. Then it says anecdotal evidence for H1. And if it's 1/10 to 1/3, that's 0.1 to 0.333. Then that's moderate evidence for the alternative hypothesis. So it's kind of giving you a grade here. In SPSS, larger Bayes factors indicate more evidence for the null hypothesis. It should be noted that in other analytical programs, the opposite interpretation may be made. And in the above table from the SPSS help system is provided to give users some guidance as to how to interpret it. So if I go back and rerun this procedure again, you can see I can say estimate Bayes factor this time. It goes and reruns it. And now it's giving me a Bayes factor of 8.441. Now remember, let's go back here. Let's look at this. 8.441. So it's between 3 and 10, isn't it? So moderate evidence for the null hypothesis. That's what we're saying. So using the same analytical examples before, we can see that based on this Bayes factor of 8.441 provides moderate evidence for the null hypothesis that there is no difference in the average amount of previous experience for clerical and managerial workers. Now, at this stage, I do think I really should do something about this prior stuff because I haven't really talked about these prior probabilities. I haven't played around with them. I just wanted to point out how you would do that. If I click on both methods here, I'll just get output from both methods. It shows me the credible intervals, which are shown down here, the credible intervals, and it shows me the Bayes factor. So you get credible intervals and Bayes factor. You notice it is throwing in a significance test here. So this does do a p-values, but that's because it's kind of lost. They kind of lost their nerve and said, "Well, I got to put in a significance test as if it was a frequentist test." That's not Bayesian in nature, really. But it is a good indication. If you're getting too confused over this, then the significance value will give you a bit of guidance. Obviously, if it's less than 0.05, it means it's in the frequentist world significant, and if it's greater than 0.05 in the frequentist world, it means non-significant. But if I went back here, I could go into this and I could say, look, I can go into the priors, and there's some data here where I can put stuff in. For example, I could tell it what the variance is for group 1 and group 2. The variance is actually the square of standard deviation. So if you looked at the standard deviations there and you squared them roughly, you could say, I happen to know that the variances should be, 10,000 and 6,000 for these two groups. You just take the standard deviations and square them. And it produces, as you can see here, because I'm now telling it what the variance should be and kind of pre-informing it with some data. But if I could also go down here and I could go to priors and I could say, okay, this is a norm. I'm going to give it some location and scale parameters. Location refers to, in this case, the mean, and the scale refers to the standard deviation. So for group 1, I know it's annoying that it's the standard deviation, not the variance, but that's just how it's been implemented. I'd say location for 1 is, I'm going to assume it's a mean of 80 of a standard deviation of 90. And for group 2, I'm going to assume it's a mean of 75 and a standard deviation of 75, let's say again, 75. And immediately when you do this, what you notice is the prior charts now are different. Yeah, so we've given it some prior probabilities, which are not non-informative probabilities, actual probabilities. Now, in fact, here we don't reach different conclusions. This is still minus 22, a negative number and a positive number across the credible intervals. And the Bayes factor is pretty much the same as before, 8.441. So it hasn't made much difference at all. It indicates just how strong the data is and how robust it is against giving it prior probabilities. But it does mean that you could play around with it and say, well, some studies say that the priors should be this, and maybe the difference is the mean value for this group should be lower, and the standard deviation should be higher. And it allows you to play around somewhat with these prior values, prior probabilities, to see the effect on the test that you're doing. Something which, of course, you couldn't do in the frequentist approach. Okay, I would just point out that there's a very good book here for recommended reading as we come to the end of this, The Art of Statistics by David Spiegelhalter, which does talk at the end about Bayesian statistics. He's a bit of a fan of Bayesian approaches. It's a really good book if you want to start with the absolute basics of stats, and it goes to a fairly sophisticated level, keeps you on the straight and narrow, and tells you how to interpret things and explains, why people misinterpret stuff. I find it very, very useful. And you should be aware that we do offer a range of consulting services, which take the form of analytics advice or project support. Could be one day, could be longer engagement, could be where we analyze your data, or we analyze your data and then teach you what we've done, work alongside you. Against that, we also provide direct sourcing of the SPSS software. We sell that ourselves. We can assist with the selection, pilot, and implementation of analytical tools. that matches your own. We can provide training services, whether it be in classroom or virtual training services. And we can also provide identification and recruitment of analytical skills in your organization. We generally offer no strings attached technical and business advice relating to all things analytical. And we offer formal technical support services to our customers who are using the SPSS software. I do hope you found that useful, and we look forward to you logging in again. If you check our website, you'll be able to see the forthcoming roster of webinars that we've got coming up in the future. We'll also find that if you go onto YouTube, we've got recordings of many of our previous webinars and shorter recordings of look at particular techniques. So it's worth exploring if this has been useful to you. Thanks very much, and we look forward to logging in again.